Welcome, everyone. It's really good to see the geoscience people back at the Science Library. Welcome, very, very warm welcome. This will be our first Geonsdag, Geo Wednesday, this fall semester. And Professor Thomas Vikhammar Schuler will introduce our presenter today.
Thank you, and welcome once again. So it's my pleasure today to introduce Regine Hock, our speaker today. She's a professor at the Department of Geosciences at our university. And a bit about her background. She holds a master degree in hydrology from University of Freiburg in Germany. That's where I come from. And she was already finished with that when I started my studies. Then she moved on to ETH in Switzerland and took a PhD there. I did more or less the same after my career, but she had already gone when I came to Zurich. And then we were a bit more synchronized when she was working at Stockholm University, and after my PhD I was working together with her in the same project. So we are synchronized, and then she left for Alaska and was their professor at the Geophysical Institute at the University of Alaska Fairbanks. And I started my career here. So that's from going lagging behind to being synchronized. I'm happy actually that I for once was actually ahead. But since 1 year, Regine is also at our department. She has been working a lot on that interface between hydrology and glaciology, has developed a melt and mass balance and energy balance model for Glacier, and has been working on problems related to glacier changes and response to climate change, both on local, regional, and also global scale. There's a long list of merits, so I'm not going to repeat all of that. But some of the most recent was she was a coordinating lead author for the special report on ocean and cryosphere by the IPCC. And she was a very active member in the Glacier MIP, the Glacier Model Intercomparison Project by CLIC. And I think that is a bit that sets a bit the stage of what she's going to present here. And so I would like to hand over to Regine.
Okay, Thomas, thank you for the introduction, and also thank you for coming and for having the opportunity to speak to you today. Land ice is melting worldwide. What you see here is a time evolution of the mass changes of the ice sheets in Greenland and Antarctica since 2002. The colors show their annual thinning rates on the map. And the ice sheets were more or less in balance a few decades ago, but they have been losing mass at an increasing rate. There's large regional variations, there's large thinning at the ice sheet margins, and in Antarctica, in particular here in West Antarctica. But in this talk, I will not talk about the ice sheets, but about all glaciers in the world outside the ice sheets, but including those that are in the periphery of the ice sheets, that are not connected to the ice sheets around Greenland and Antarctica. So that's about 200,000 glaciers. They cover an area of 700,000 square kilometers, and just to put that into context, this is the area of Norway and Sweden and Finland together. And if you melted all the glaciers, that is an approximate sea level equivalent of 40 centimeters. So sea level would rise 40 centimeters if you melted all these glaciers. So what I want to do in this talk is talk about how have glaciers changed in the past decades, how will they change in the future, and why does it matter? So worldwide, these glaciers have retreated and thinned and lost mass over the last century. Here's an example from the European Alps. Or here's some other example from Alaska, sort of huge mass changes over the last decades. Or here another example from Argentina. So dramatic changes just in the last decades. What is new now is that there's large changes just within a few years. So in the last few years, you can just go back again here. So huge changes just during the last 1, 2, 3, 4, 5 or so 6 years. Here's another example. Also huge changes here at Finderling Glacier in Switzerland just during the last years. So the mass loss has accelerated. Already decades ago, it was recognized here in this seminal paper that these glaciers outside the ice sheets are a major contributor to global sea level rise. Here Meyer, he concluded that between 1900 and 1961, these glaciers contributed about 1/3 to half of the observed sea level rise during this period. And that is a quite remarkable finding at that time, because at that time there was very, very little data. But all subsequent studies have confirmed the large role of glaciers in the sea level budget, the glaciers outside the ice sheets. So these glaciers outside the ice sheets, they make up about 1% of the world's ice volume. But there are major contributors to sea level rise. They contribute more to sea level than Antarctica and almost as much as the Greenland ice sheet in this period here, 2006 to 2015. And approximately 1/4 to 1/3 of the observed sea level rise in recent years and decades comes from these glaciers outside the ice sheets. And the total sea level rise about 3 millimeters per year. What you see here is the result of studies about global mass changes. So here's a time series of mass changes per year. That's the curve in black. The gray is plus minus the uncertainty. And the boxes are other studies that show an average over multiple years plus minus the uncertainty. And this is done here for globally, for all glaciers, and separately for all glaciers, but excluding those in the periphery of Greenland and Antarctica, and I show that just because there's a lot more studies. But what they have in common, there's some differences between the studies, but all show substantial mass loss over the last decades. And they show an increase in mass loss in recent years. This is here the global scale. When we look at here the same type of graph, but for all mountain regions separately. Again, you see a time series of annual mass change in gray, and superimposed are multi-year estimates as boxes from different studies. And what is important to note here, there's huge year-to-year variability about mass loss. You can have a year with even a mass gain and followed by a year with a lot of mass loss. And there's huge spatial differences, regional differences. For instance, some regions here in high mountain Asia, the mass loss is about 20 centimeters per year thinning. Also, relatively little thinning rates here in Svalbard or Greenland, or here in the Russian Arctic. But in other regions, like Central Europe or low latitudes, we have thinning rates of more than 1 meter per year. So it really varies where in the world you are. So what are the reasons for this global mass loss? Air temperature increase is the main driver. Locally, there are other meteorological variables that modify the response of the glaciers to climate change, but it's really air temperature is the driving force. And looking about how much is the anthropogenic effect, there's a study showing that the anthropogenic driver is about 60% of the mass loss in this period 91 to 2010 is due to anthropogenic climate change. And this has increased dramatically compared with the previous period here of more than 150 years. So almost all glaciers in the world retreat, but some advance. And why is that? And these glaciers often receive a lot of media attention. and the advance is misinterpreted. I mean, first of all, this is only very few glaciers globally, and it's often unrelated to climate. There's essentially three principal causes of such glacier advances that can happen even in a warming world. There is climatic causes. Here, Briksdalsbane in Norway was advancing in 1997 and a few years after that. This was the first time I was in Norway, and it was really exciting to see this glacier running into a forest, and here the people are running away from the advancing glacier. These advances were due to an increase in more snowfall. Even though it gets warmer, there was just a few years of a lot of snowfall. In New Zealand, at the same time, glaciers were advancing too, like here Franz Josef Glacier. But in this case, it was not an increase in snowfall, but a local cooling just in New Zealand where these glaciers were. So there are some climatic causes for these advances that are usually local, but also not lasting. In both cases, it has gone back to retreat. But there's also other reasons for glacier advances, and that's dynamic causes that are unrelated to climate. And this is especially the case for glaciers that end up in the sea, in the ocean. We call them tidewater glaciers. For instance, Hubbard Glacier here in Alaska, it's a huge glacier, several thousand square kilometers large, has been advancing for decades. Another example here is Taco Glacier, also in Alaska. It has also been advancing for decades, going here into this forest. Tourist boats went there decades ago, almost 100 years ago. Here in 1934, a boat with tourists, but they were right in front of the glacier. But the front of the glacier was right here in 1935. Now this is hundreds of meters of ice where this boat was like 80 years ago. I mentioned Hubbard Glacier and Taco Glacier, they're advancing, but at the same time, you don't go far away from these glaciers. Columbia Glacier here has been retreating rapidly, 20 kilometers in a few decades. And that is typical of these tidewater glaciers. They can be in close proximity. One is advancing and one is retreating. Here's a summary of all tidewater glaciers in Alaska, and what you see is the relative length changes. The length here in 1950 or so, and then you see how the length changes. Negative means it retreats, and positive means it advances. And what you see is a very, very complex pattern of glaciers retreating and advancing. Some glaciers have like oscillations. They retreat, advance. Other glaciers advance, and then, like Columbia, has a rapid retreat. Here another one with a rapid retreat, and now, the last decades, it's advancing again. And that's typical of these glaciers, and that is also consistent with theory. So it has been, the idea here is that these glaciers undergo natural cycles of a slow advance. They advance in shallow water over hundreds of years, and usually pushing here a moraine in front of them. And then there's a rapid retreat. And important is that these glaciers can advance and retreat without a change in climate. It's really just internal dynamics. This is your simulation. And you see the glacier advancing here, pushing that moraine in front of itself, and that stabilizes the glacier. But as soon as it starts retreating, it gets into deep water and rapidly retreats. And I want to emphasize again, this is without climate change. In that model, the climate is constant, but the glacier is advancing and retreating. Another reason why glaciers advance is surging glaciers, surges, which is usually a short phase of strongly accelerated glacier flow velocities that can lead to an advance. Like here, also in Alaska, the glacier was right here, and just a year later, it had advanced 3 kilometers. Only about 1% or less of the glaciers in the world surge, And again, this also has to do very little with climate, but is due to changes in the basal conditions, mostly the drainage system under the glacier. So it's largely unrelated to climate. Or another example here of a surge advance in Svalbard, and just a year later, an 8-kilometer advance. Just some fun numbers here. The greatest recorded surge advances are 21 kilometers for Svalbard Glacier and 12 kilometers in a just 2-month period of a glacier in Karakoram. These advances can also lead to glacier hazards and catastrophic glacier outburst floods. Here, the surge in such an outburst flood is even documented here back to like 1601, or another one in 1772 here in the European Alps. The glacier was suddenly advancing, blocking that valley, a lake formed, and the lake drained. So just to summarize this part here, glaciers are losing mass worldwide due to climate change, in particular warming. The worldwide thinning rate is 85 centimeters per year in this period here, 2006 to 2015. So just imagine, over the entire area of glaciers worldwide, they are thinning 85 centimeters every year. And just to emphasize again, advancing glaciers are the exception. And these advances are caused sometimes by local climate changes, but mostly by internal glacier mechanisms that are unrelated to climate. So how will glaciers change in the future? For projections, we typically use glacier models that are driven by temperature and precipitation, using a number of climate models, and which are forced by different emission scenarios. So in the past, a lot of these RCP emission scenarios have been used, and what you see here is how these emission scenarios translate into temperature and precipitation changes. So you see here the time series of temperature and precipitation for two end members of a low emission scenario up here and a higher emission scenario. And you see it both for the global temperature in green and only over the glaciarized area. So here for the high emission scenario, over the glaciers, there's a temperature increase projected of 6 plus minus a few degrees. And what is important to note here is the temperature increase projected over the next century is much larger over the currently glaciarized area. Many individual glaciers have been projected into the future. Here's an example of the largest glacier in Switzerland, Aletsch Glacier. And even for the low emission scenario, the glacier is dramatically reduced. For the high emission scenario, it is essentially disappearing. Here we did another simulation of the Juneau ice field in Alaska, also for the next 100 years, projecting the mass losses. And you see also dramatic decreases in volume and area of this very, very large ice glacier. I mean, this one is about twice the amount of ice that there is in Scandinavia altogether. The volume losses are large, but there's still ice left over at the end of the century. But this ice field is less susceptible to climate warming than other ice masses in the world or in Alaska, because the glacier can retreat to higher elevations where it's colder. So that's why you have still these mountains here sticking out, and that's where the glaciers can survive. This is very different in other ice caps, very close by, that are low-lying ice caps or ice fields where the glacier cannot retreat to higher elevation. And this is, for instance, here an ice field of more than 600 square kilometers is projected to disappear even if there's no climate change, so within the next 100 years. So even just keeping the climate constant, it is disappearing because it's low-lying, cannot retreat to higher elevation. And under climate change scenarios, it disappears even much earlier. So here you see the regional mass losses of all glaciers in the world for 19 glacier regions. What you see here is the mass loss in percent relative to now by the end of the century. So here for Central Europe, and each dot is one glacier model, a multi-GCM mean, and the triangles are the mean of all the projections. In total, more than 200 projections using different models. So here for Central Europe, the projections are that 80 to 100% of the ice is disappearing by the end of the century. But there's huge differences depending where you are. In other regions, like here Arctic Canada, the mass losses are about 20% of the current volume. And essentially, it's a little bit like sorting these regions by glacier area. Central Europe, low latitudes, Scandinavia, there's not a lot of ice. Those regions are losing almost all their ice by the end of the century. Whereas the regions where there's a lot of ice right now, like Alaska, Canada, Canadian Arctic, Russian Arctic, they're losing only 10, 20, 30% of their current ice volume. These mass losses translate into sea level equivalent, sea level rise. And here the picture is very different. The regions that lose very little relatively to today are the largest contributor to sea level rise. And that's just because there's so much ice, there's such a large area of ice over which this thinning is occurring. Whereas the regions that lose almost all their ice, they're pretty insignificant when it comes to sea level rise. So the sea level contribution comes from a few polar regions, mainly from really a few polar regions. But in these regions here, where the glaciers are almost disappearing completely, these mass losses are important for other causes, for instance, for hydrology, for stream flow. Here you see the relative mass losses of the latest results from the International Glacier Model Intercomparison Project, more than 280 simulations from 11 glacier models and up to 10 climate model scenarios. And you see it here globally and for all the 19 regions again. So one is 100% mass right now, and then how much is left over by the end of the century. Globally, the glaciers lose between 17 and 38%, depending on the emission scenario. Low emission scenario, high emission scenario. That translates into about 75 to 170 millimeters by the end of the century. And then looking regionally again, same picture here. The regions with a lot of ice have the relative mass losses are 10, 20, or 30%, whereas the regions with little ice, almost all the ice in many of the simulations are almost about to disappear. You can also express these mass losses here in specific units, in kilograms per square meter. And that is, 1,000 kilograms per square meter is 1 meter thinning in water equivalent. So this tells you how much the glaciers are thinning per unit area. And what you see here is quite interesting. For the RCP 2.6, the low emission scenario, actually the mass losses here become less. The thinning rates become less with time. And that might be counterintuitive, but it is because many glaciers will disappear, but other glaciers will retreat to higher elevations and stabilize. Because at higher elevation it's colder and they can stabilize and find a new equilibrium. That means there's less mass loss coming from these glaciers. So even though we have some climate warming, here the mass losses, the thinning rates become actually less. This is different for the RCP 8.5, the red curve here. The warming is too intense. The retreat cannot compensate for the warming, and these thinning rates increase everywhere in the world. So massive increases in annual thinning rate, how much it's thinning every year. Here, for instance, Canadian Arctic, 2,000, that means 2 meters of thinning every year. Svalbard, is about 6, 7, 8 meters of thinning every year at the end of the century. So we have very, very large thinning rates here in these regions, like Svalbard, Arctic Canada, Russian Arctic. Relatively also an increase, but less intense thinning rates. Oops. Less intense thinning rates here in these areas with, where there's little ice. And that has to do with the geometry of the glaciers. Here in Svalbard, Arctic Canada, Russian Arctic, there's a lot of ice caps. The glaciers cannot retreat to high elevations because the glacier, the ice cap itself, is the highest elevation. And as soon as it starts thinning, there's a positive feedback. It's digging its own grave because it becomes lower and lower where the temperatures are higher, and that intensifies the melting even more. This is why here Svalbard is the region where we project the highest thinning rates at the end of the century, 8 meters per year. Whereas here in these regions that have a little ice and often smaller little mountain and valley glaciers, the glaciers can retreat to higher elevations and stabilize, even though, of course, many will also disappear. When we look at the sea level contribution, for the low emission scenario, the sea level contribution, how much water is coming from these glaciers, is actually going down. And that is because the glaciers can retreat to higher elevations, and also many glaciers disappear, so that is, the contribution goes down. But for the high emission scenario, and the world is on this track here, the contribution to sea level rise will increase throughout the century. And what I really want to point out here is at the end of the century, the sea level contributions per year are similar to the current total sea level rise. Total sea level rise at the moment is about 3.5 millimeters per year. And it comes from thermal expansion, the ice sheets, glaciers, and other sources. So by the end of the century, the glaciers outside the ice sheets alone are contributing as much under the scenario as the sea level rise that we have right now. So why does it matter? So what are the impacts? I mentioned sea level, but there's a lot more impacts. Stream flow, hazards, landscape changes, and so on. When glaciers change, stream flow changes. What we've seen from data and simulations is there's massive increases in daily runoff maxima when a glacier changes from equilibrium to very negative mass balances. Here's the river here in Austria, in a highly glaciarized area. In a period of a balanced mass budget, the runoff was maybe 2 cubic meters per second. And this is when this research station was built. 20 years later, after years of very, very negative mass balances, the runoff is like the peaks are 10 times as high. And one of these peaks washed away the station. So there's really a risk for floods, especially if combined with strong rain. There's an impact on annual runoff. So as the glacier retreats here, first, runoff will go up. There's more water coming from the glacier. And sometimes 50, 60, 70% more over the years. But as the glacier retreats even more, this reservoir is depleted and the runoff will go down. And we call this timing, when this happens, this turning point, peak water. And that's, of course, extremely important for anybody operating a hydropower facility in a glaciarized catchment or any water resources management. You want to know if you can expect more water or less water in the next decades. So we looked at peak water here in the IPCC SROC report. You see here a compilation of all published studies about peak water. The bars are a modeling study computed for every single glacier in the world. So essentially what it means is how much area here reaches peak water in which decade. So here, for instance, 50% means that 50% of the area in the low latitudes has reached peak water already because it's before today. And the bars add up together to 100%. You also see then any other studies that are published in the literature showing when peak water occurs in some sub-regions in these regions. But the basic message here is that peak water has already been reached in regions with little ice cover, in many parts of these regions. So that means here, low latitude, Central Europe, Western Canada, that the runoff in many of these areas is decreasing. There's less water coming from the glaciers. Peak water here in Scandinavia, high mountain Asia, in most regions it's reached by the middle of the century. So in some regions it's still going up in Scandinavia, and other regions it's going down. And peak water is reached latest in regions with a lot of ice, like Alaska, southern Andes, where essentially the runoff from the glaciers is increasing over the entire century. But in all regions, peak water is reached by the end of the century for all climate scenarios. So then the water that's coming from the glaciers, this reservoir is exceedingly depleted, and the runoff goes down. You can also look at it a little bit more differentiated. Here's the study we did in the high mountain Asia for different emission scenarios. The color tells you when peak water is reached, where. And you see it very varies. It depends where you are. In the monsoon-fed rivers, here in the Ganges and Brahmaputra, peak water has already been reached for all scenarios. Whereas here in the westerly fed rivers, the Indus, for instance, in some regions, peak water is reached at the end of the century, whereas really at nearby catchments, it has already been reached. So it depends really where you are. But this information is important for anybody who's doing water resources management, or any power companies or irrigation or any purpose, any people who are using glacier water for their management. Glacier retreat destabilizes mountain slopes. Here, rockfall after a massive thinning of a glacier here in Switzerland. So there's a risk for more landslides and rockfalls. Decrease in glaciers lead to an increase in the number and size of lakes. Lakes form in over-deepenings when the glacier retreats, and these are dammed by moraines, and the moraines are not stable. So there's a risk for these lakes to drain, so-called glacier outburst floods, and those are some of the most devastating glacier hazards. So because of the retreat, formation of lakes, there can be an increased risk of these glacier outburst floods in the future. There's an impact on landscapes, and with that on tourism. Like here, Juneau, the capital of Alaska, has 10,000 inhabitants, but 500,000 people visit every year on cruise ships. And the only thing they do in their 3 hours they have in Juneau is go to this glacier, take tons of pictures, and go back to the boat. The glacier, I showed the simulation earlier, it's the Juneau ice field. The glacier is retreating around the corner in a few decades. It won't be visible anymore from the visitor center. So there's an economic impact on tourism as well. There's an impact on cultural values. The glaciers are among the principal sites or the principal reason or secondary reason for more than 30 World Heritage natural sites. And the projections show that the glaciers in half of these World Heritage sites lose their glaciers by the end of their century. So they lose the reason why there are World Heritage sites in the first place. The glacier retreat has an impact on spiritual values and belief systems in many parts of the world. Here are examples from Bhutan and Peru. The retreat and disappearance, research has shown, can have an impact on the well-being of the people who live there in these native populations. The retreat of the glaciers has also some positive impacts. It's a unique source for historians because all kinds of things are, in recent years, are melting out of glaciers. Also here in Norway and Alaska, all kinds of artifacts that were buried and are extremely well preserved in the ice are melting out. And so much artifacts have been found, melted out of glaciers that even a new journal in Arctic archaeology has been launched. And of course, very famous is here the Ötzi in the at the Austrian-Italian border that was found two decades ago, sort of a Stone Age man, 5,000 years old. So of course, I mean, a unique resource for historians. But not everything that comes out of the glacier is good. There's also, with the increased melt of glaciers, there's a release of contaminants. There's anthropogenic legacy pollutants coming out of the glacier. And that can have a possible impact on water quality of downstream systems and ecosystems. And that is, there's not much research about it, but it's certainly a field that deserves some attention. So going back to my first slide, will there be any glaciers in 100 years? Globally, yes. More than half of the ice is likely to be left outside the ice sheets. And that also means that these glaciers outside the ice sheets are not going to be gone in 100 years, but they will continue to contribute to sea level rise. But in some regions, and that includes Scandinavia, more than 80%, if not all glaciers, will have disappeared by the end of the century, under the more aggressive emission scenario, the scenario we are on. So I just want to conclude. So glaciers around the world have lost and will lose substantial ice volume by the end of the century. Many glaciers will disappear completely. Some glaciers will advance, and I just want to emphasize that again because it's often taken up by the media. It's for reasons, in most cases, reasons unrelated to climate. The impacts are on sea level, streamfall, water quality, cultural values, but in a nutshell, it's really glaciers are losing mass rapidly, and this impacts people around the world. Okay, thank you very much for your attention, and happy to take any questions.
Thank you, Regine. And yeah, you have answered your question that you put up in the title. If you remember, maybe, well, you might be interested in how the glaciers in Scandinavia and especially Norway are doing. You might remember that the uncertainty span was quite wide. So there is, on one end, that means there is hope. So glaciers can retreat to higher elevation and they can survive. But for some emission scenarios, this is just not high enough. So there's huge uncertainty. Yeah, but that gives also some hope that, well, we still can do something about it and preserve some of the glaciers. Regine, we have some minutes left for questions. Due to pandemic reasons, we don't pass around the microphone. But if you ask out of the audience, I can repeat the question. So then it's available for everyone.
Maybe it's a stupid question, but I see Glacier as a storage of coldness. What happened to the climate regionally when it disappeared? When the glacier was cold in the region, and when it disappeared, it did not be cold anymore. So what happened to the climate regionally?
So the question was about the, you can see the glaciers as a cold reservoir. So, and if this cold reservoir depletes, how would that affect the climate in the surroundings of the glaciers?
This is a very good question. It's not stupid at all. There is a connection. The glacier, because it's cold, is also cooling the local climate. So if the glacier disappears, this cooling mechanism is not there anymore, so it becomes even warmer locally. The question is if this is really has an impact on a larger region or globally, and that there's research showing that is certainly the case for like the Greenland and Antarctic ice sheets. If they disappear, the climate will become warmer, even globally. But locally, if small glaciers disappear, the local climate will change. It will become warmer because you don't have this cooling ice lying in the valley anymore.
I have a very similar question. So regarding the radiative budget, as in the first question, is it taken care of in your glacier models if they are not run coupled with the atmosphere, that the radiative balance is changing due to albedo change when the glacier retreats?
Let me repeat the question. So the question was whether your glacier models also account for the radiative balance, and and how that is taken care of.
No, they don't. We take the climate scenarios from the climate models, but the question can be asked the other way around. Do these climate models include the glaciers and the changes in glaciers? And there's still a lot of work to be done because some of these climate models don't include, for instance, the glaciers that are around the ice sheets, that are other than the ice sheets. So which essentially would lead to even more warming if that was included.
Yep, Hans-Peter.
What about precipitation? I mean, a warmer climate obviously will cause the ice to melt, but it will also cause more precipitation. Is that included in the models?
Yeah, the question was whether precipitation changes that are expected, so increasing precipitation, could compensate for increasing mass loss by temperature increase.
That's a very good question, and it is true. There is, and if you maybe remember that one slide I showed about the temperature and precipitation changes, precipitation is going up and there will be more snowfall, so it is partially compensating for these temperature increases. But all studies have shown that on average, a 1 degree temperature increase is not even closely compensated for by like a 10% increase in precipitation. So temperature is really the main driver, and the precipitation increase is only very to a small degree compensate for that increase. Except locally, what I showed about Briksdalsbreen, I mean in the 90s in Scandinavia, where really there was a lot of temperature precipitation increase that actually counteracted the increase. But globally, temperature is the driving force of the mass changes.
May I also add to this question? So I was wondering about the glaciation process of snowfall. Like how well is this represented in the models? How fast or how slow the snow becomes glacier?
The question was about how we can account for the time delay it takes for snow to form glacier ice.
There's sort of a whole range of models. There's very simple model. When you work on a global scale, you cannot take that into account. But other processes are more important, and you really look at just the melt, no matter if it's snow or ice or what it is. But then there's models that are more detailed and often apply to an individual glacier that look at essentially include all the physical processes, including like the densification of snow and transformation into ice.
Good. Well, thank you again very much, Regine. And before closing this session, I would like to make you aware of the next Geo Wednesday, Geoonsdag, that will be 20th of October with Ingrid Anel. And I am convinced there will be a title will be communicated with you in time. Thanks again.
Und 50.